Here we're going to be talking about molecular geometry and the valence shell electron pair repulsion model, sometimes called VESPR, even though it's VSEPR. We'll talk about the different geometries. So we have molecular geometry, but also electron domain geometry, sometimes just called electron geometry. There are ideal bond angles associated with these different geometries. There are some deviations that we'll want to learn. And there's also, we'll talk about geometry of molecules when they have more than one central atom. A lot of the Lewis structures we've dealt with so far have just one central atom, and those are simpler situations. Then lastly, molecular geometry and how that deals with polarity. So valence shell electron pair repulsion model, VESPR. The reason we care about this is this will ultimately be a way in which we can predict the geometry of these atoms and their orientation to each other. This really does affect their chemical and biochemical characteristics. So depending on the individual molecule, the way in which they are assembled and their three-dimensional structure will really affect its chemistry. So this is why we ultimately care about this. We can predict the shapes of these molecules using this valence shell electron pair repulsion model, starting with a Lewis dot structure. The very basis of this model is that these electron pairs in the valence shell of an atom repel each other. So valence shell electrons, these repel each other, and that's where you get the valence shell electron pair repulsion model. An electron domain or an electron group is a lone pair or a bond, regardless of whether the bond is single, double, or triple. So when we talk about electron domains or electron geometries, we're really just concerned about how many groups are off of the central atom, and it does not matter whether it's a lone pair or some sort of atom, which would have a chemical bond associated with it. So here are some examples. Here's CO2, and you can see we have CO2, ozone, and ammonia. Each of those have the Lewis dot structure associated with them that we've already made. So if we're unfamiliar with Lewis dot structures, we still need to make sure we know how to do that before we can start using VESPR theory. You can see there's two electron domains in CO2, even though they're both double. So there's an oxygen on one side and an oxygen on the other side. There are no lone pairs on the central carbon. So this means there's only two electron domains total. When you go to ozone, however, that central oxygen has three electron domains. We have the two bonding domains, the oxygen on the left, the oxygen on the right, and one lone pair on the central oxygen. Again, these geometries, we really care about the internal atom. That central atom will be the one that predicts these geometries. Then lastly, ammonia. It has three bonding domains, which are those three hydrogens, and then one lone pair. So it has four electron domains total. These have names associated with them. So CO2, so whenever you have two electron domains, the electronic geometry is linear. If you have three electron domains, the electronic geometry is trigonal planar. If you have four electron domains, the electronic geometry is tetrahedral. We can actually go a little bit beyond this. There are 5 electron domains and 6 electron domains. These are the only 5 electron domains that you can have: 2, 3, 4, 5, or 6. So here we have an example of 5. Remember, 5 and 6 now means that you have 10 valence electrons around the central atom, or 12 at the very least for 6 electron domains. So that means the central atom in those situations have to be able to break the octet rule. So if you have, for PCl5, here you can see you have 5 single bonds, so there are 5 electron domains. This is called trigonal bipyramidal, which is a little bit more of a rare one. And then lastly, we have 6 electron domains. We see that there's 4 single bonds and 2 lone pairs, so that's a total of 6 electron domains. That means the electronic geometry for this is called octahedral. And that is, again, quite a common one, especially when we deal with larger and larger atoms. So valence shell electron pair repulsion model, this predicts these electron domains will repel one another. So they will arrange themselves as far apart as possible, which will minimize those repulsive interactions between them. So if you have just two electronic domains like this, like over here, you have, they're going to line up directly across from each other if this central location is the atom's location. So this is what we call linear. They're 180 degrees from each other. They're as far apart as possible. Now we go up to 3 electron domains, and that's represented by these 3. And this is what we call trigonal planar. It's on the same plane, and trigonal meaning 3. So these are each 120 degrees from each other. So that's trigonal planar electronic geometry. Then we go up to 4. This is tetrahedral. So tetra meaning 4, so that makes some sense. Again, the central atom is here. These are all lining up as far apart as they can, and you can see it has a little bit of a bizarre bond angle associated with it. The ideal bond angle here is actually 109.5 degrees. Okay, and then 5 and 6, and you can see that these have different geometries as well. This is called trigonal bipyramidal. So trigonal meaning you have the same sort of trigonal setup like you did here with these 3. And then you also have kind of a linear setup above and below like this. So it's kind of like you're combining these 2 together to get this. And these will actually have the same bond angles as you observed in these 2 situations. Then lastly, you have octahedral, which is 6. I know octa means 8, but an octahedron has 8 sides and 6 vertices. These are representing the 6 vertices. So that's how this gets its name, but this is octahedral geometry. And you can see that these are actually all mutually 90 degrees from each other. So this is what we mean by the valence shell electron pair repulsion model, where we can use this idea that these electrons are trying to get as far away from each other as possible to help predict the geometries that we would expect. Okay, this is what I just mentioned in terms of the ideal bond angles. So we have linear, which is 180, trigonal planar, which is all 120 degrees, tetrahedral, which is 109.5 degrees ideally. Trigonal bipyramidal has 2 different bond angles associated with it. You have the top and the bottom one here, which are 90 degrees from these. These 3 are called equatorial. These are axial, so you can think of this as the axis, like a north and a south pole. These are around the equator, and there's 3 of them. So these equatorial positions are all 120, just like the trigonal planar. And then these axial ones are 90 degrees to the equatorial one, or 180 degrees from each other. So this has 2 different bond angles associated with it. Octahedral, each of these are mutually 90 degrees. So we're going to have times where we will deviate from the ideal bond angle, and this we can justify quite easily just based on what we know about electron pair repulsions. So what we know is what we're going to learn here is that a lone pair takes up more space than a bonding pair. This should be a little confusing because a lone pair is just 2 electrons, where a bonding pair has an atom at the very other end. So you'd think an atom would take up a lot more space than just 2 lone electrons, which we know electrons are tiny. But on the flip side, electrons are full-blown negative charge. If it had an atom at the other end, that has a nucleus and a positive charge. So if we're just dealing with electrostatic repulsion, lone pairs actually are more negative than a bonding pair. So they will push other electron pairs away from them more strongly. So these lone pairs contain a more electron density. So even also multiple bonds. So if you have a double bond or a triple bond, those will repel other electrons more strongly as well. So you can see some deviation. So here's ammonia, NH3. There's a lone pair right here. Okay, and this lone pair takes up a little bit more space. So ideally, this was a 109.5 degree bond angle, but actually these bonds are pushed a little bit closer together, down to like 107 degrees, just because this lone pair is pushing these bonds down a little bit more than what would have otherwise been the case. Likewise, here you have formaldehyde. This you have a double bond here, C double bond O, and this should all be 120, 120, 120. But what ends up occurring is this takes up a little bit more space because it's a double bond. It has more electrons associated with it. And that'll push these two hydrogens just a little bit closer to each other than what would have happened otherwise. So instead of 120, this becomes 116 degrees. And therefore, this increases just a little bit to accommodate that. You can see there's some other examples of this as well that can occur. There's a lone pair off of this side that will also then decrease these bond angles just a little bit. And likewise, there's a lone pair right here. So going just a little bit below 90 degrees, you end up pushing these up just a little bit. All right, so this, what we've been talking about is the electron domain geometry. And again, I just call this electron geometry. And this is just the arrangement of the electron domains, whether it's a bond or a lone pair around the central atom. A molecular geometry is similar, but it will pertain more to the arrangement of the bonded atoms. So if you take a look at this situation for ozone, we have electron domain geometry is trigonal planar. It has three domains off of it. This oxygen, and a lone pair. So it's trigonal planar. There are three electronic domains. But if you look at its actual geometry, this it's not that we ignore this this lone pair that's up top here. It affects the geometry, but we're not really going to talk about it in terms of the number of kind of domains here. So the molecular geometry here is actually bent. And we'll see what this looks like for some other geometries as well. Here are a bunch of them. Here we have the total number of electron domains, and these are just some common ones that I think are challenging. So if you have 3 electron domains, this is called, the electron domain is trigonal planar. If you have 4, this is always called tetrahedral. If you have 5, trigonal bipyramidal. 6 is octahedral. If you start adding lone pairs, this is excluding times where you don't have lone pairs. If you have 0 lone pairs, the electronic geometry will be the same as the molecular geometry. But here, if one of them is a lone pair, we have a bent situation. For here, we have a tetrahedral geometry. If we replace one of those locations with a lone pair, it becomes trigonal pyramidal. Okay, so it makes this little pyramid. This was this NH3 situation. So that lone pair is taking up space up here, which will push down these hydrogens. Okay, and you can see there's a bunch of other ones. We have another scenario where it's bent. This is like water. You have a tetrahedral geometry, but 2 lone pairs on the central oxygen. And this is why those hydrogens are bent downwards like so. So you actually have bent molecular geometries with multiple electronic domain geometries. You can see it gets more complex as we go. These are going to be some more challenging ones in general, just once you have more objects to deal with. I like this table maybe just a little bit better because it gives you every iteration. So here, if you have 2 electron groups and there's 2 bonding groups, that's linear. So CO2 is a good example of that. Here, you have 3 electron groups. So this is called trigonal planar for the electronic geometry. It's also called trigonal planar for the molecular geometry if you have no lone pairs. Again, the electron geometry and molecular geometry will be the same if you have no lone pairs on the central atom. However, if you replace one of these bonding pairs with a lone pair, that trigonal planar becomes bent, which is what we had already talked about. This will affect the bond angles. So here we had 120 degrees for trigonal planar. Once you added that lone pair, now you're a little bit less than 120 for this bond angle here because that lone pair is taking up a little bit more space. Okay? And we'll see the same thing now with tetrahedral. So tetrahedral means 4 electron domain geometry. So there's tetrahedral for all of those. If you have no lone pairs, the electronic geometry and molecular geometry are the same. The ideal bond angle was 109.5. Methane, CH4, is the classic example of that. No lone pairs on the central carbon. However, you could replace one of those lone pairs with, or one of those bonding pairs with a lone pair, and now you'd get this. You still have 4 electron groups, so it's tetrahedral. You get trigonal pyramidal because you now have that 1 lone pair. And now this is slightly less than 109.5. And in fact, this was 107. So all you would need to know is that it's less than 109.5. You do not need to know the exact bond angle, as it'll change just a little bit, but less than 109.5. Okay, and then you could replace even another one of those bonding pairs with a lone pair, and you get a water situation where your tetrahedral electronic geometry, but your molecular geometry is bent. And this is also less than 109.5. This is even more so bent closer to each other. This ends up being 104.5 for water specifically. But again, all you need to know is less than 109.5. So these are electron groups 2, 3, and 4. Remember there was also 5 and 6. So 5 and 6 are these situations. Here we have 5 and 6, and there are a lot of geometries here. So this is where I think it gets more challenging, especially with 5 electron domains, which is all called trigonal bipyramidal, not trigonal pyramidal. That was slightly different, right? Trigonal bipyramidal. And again, trigonal bipyramidal, same if there are no lone pairs. You can start replacing those bonding pairs with lone pairs to have 1 lone pair, 2 lone pair, or 3 lone pair. You will have seesaw, T-shaped, or finally actually linear again, where you have 3 lone pairs on the central atom, and these 2 bonding pairs are as far apart as they can be. Okay, so these are the situations, and again, you're going to need to know these bonding angles, both the ideal and whether it's less than or greater than or anything like that. And that you can justify just based on knowing that these lone pairs take up a little bit more space than bonding pairs, and likewise you know about double bonds and triple bonds taking up more space than single bonds. So you do need to know these geometries, and especially with seesaw and trigonal bipyramidal, remember these do have 2 different bond angles. So when we ask to report the bond angle, you do need to say both of those bond angles. Likewise, just because it has lone pairs on it, it does not always mean that it's going to be a less than situation. So for example, here there's 3 lone pairs, and this is exactly 180, right? None of these are pushing more or less than on these fluorines. So it actually ends up being exactly linear. Likewise here, you go to 1 lone pair, and you get a less than 90 degree situation. BRF5 is the classic example of that. But once you get to 2 lone pairs, these lone pairs are exactly 180 degrees from each other. So they're not really, they're both pushing equally on these fluorines. So these fluorines are all exactly 90 degrees from each other. So it's not as simple as saying once you have lone pairs on the central atom, your bond angle will be less than the ideal. Though that often happens, that is not always true. You got to think about the molecule and what exactly is going on there. Okay. So steps to determine the electron domain and molecular geometry are as follows. So first you need to draw the Lewis dot structure or that polyatomic ion. We already know how to do that. Count the number of electron domains on the central atom. This will give you the electronic geometry. Or sometimes called electron domain geometry. I'm just always going to call it the electron geometry or electronic geometry. And that's going to be by using this VSEPR model. And you can determine the molecular geometry by considering the positions of the atoms only. You're going to be considering that based on how many lone pairs there are on the central atom, and so on and so forth. Early on, you can use the chart that I just showed. Later, of course, we're going to need to be able to do that without the chart. So let's try a few of these. Let's determine the shapes of SO3 and ICl4-. All right, so SO3, we've already done this before. First, we're going to draw the Lewis dot structure. Okay. Valence electrons, we should have 24 valence electrons for SO4 or SO3, excuse me. Just to save a little bit of time. We had done one of these before, but that was before we knew that sulfur could break the octet. So the best Lewis dot structure is actually just like this. I know you should put fill the octets of the outermost atoms first, and then you would start forming these double bonds. This is the way that you would decrease the formal charges of SO3 in the best way possible. So this is the geometry for SO3. So we'd say that there are 3 electron domains. There's this one, and this one, 3 oxygens. So this would be, the electronic geometry would be trigonal planar. And that means that these bond angles, since they're all triple bonds, this should be about 120 degrees. 120 degree bond angles. Okay. So the molecular geometry and the electronic geometry are trigonal planar since there are no lone pairs on that central sulfur. Okay. So let's try ICl4 minus. Okay. So we're going to set up the Lewis dot structure again. Okay. Again, remember this is a negative charge associated with it. So we should have 5 times 7, 35 plus 1 electron here. So this should have 36 electrons, valence electrons. I can go add them to the outermost atoms first. Fill the octets of the outermost atoms. Okay. Each one of these is going to have 8. Okay, so that's 32 total. So there should be 4 electrons left. So I will add both of those electrons to the central atom. So iodine will have two extra lone pairs on the central atom. So this has how many electronic domains? It ends up having 6 total, right? We have 4 chlorines and 2 lone pairs. So 6 was octahedral for the electronic geometry. Okay, so that was for the electronic geometry. The molecular geometry will be different than octahedral because we have lone pairs on the central atom. So we would go look at our chart. This actually ends up being square planar. These lone pairs are 180 degrees from each other. Square planar, square means that there's 4. Planar means they're on the same plane. So square planar is actually the molecular geometry here. And that means the bond angle between these would be exactly 90 degrees. Okay, so this is how we can deal with some of these, determining these electronic and molecular geometries. Sometimes you're going to have molecules with more than one central atom, so you would actually need to determine the geometry for all of these central atoms. So it would be this one, and you'd only look at the things attached to it. So for the carbon, you're just looking at the 4 things attached to it. So the carbon will just be tetrahedral, both molecular geometry and electronic geometry. It has 4 electron domains and no lone pairs. This oxygen, however, will be tetrahedral electronic geometry because it has 2 lone pairs and 2 bonding pairs. But it is bent in terms of its molecular geometry. So this is how we would deal with molecules that have more than one central atom. You just look at the very localized situation. So just what's attached to the oxygen if you're dealing with the oxygen's geometry, just what's connected to the carbon if you're dealing with the carbon's geometry. Let's take a look at one of these. Determine the molecular geometry about each central atom. So I'm going to put a mark on each of the central atoms. So it's the 2 carbons and the oxygen. And then let's take a look at the ideal bond angles. So this carbon, this first carbon on the left is going to be tetrahedral in its electronic geometry and its molecular geometry. So that means the ideal bond angle is correct. That should be 109.5 degrees. Okay. This carbon, this looks like there's 180 degrees and 290 degree bond angles. That is just the way we're drawing Lewis dot structures. That is not necessarily true with its geometry. So just be aware of that. This carbon has no lone pairs on it. It just has 3 bonding domains. So 3 means trigonal planar. And this means that all of these should be about 120 degrees. But remember, this is pushing down these bonds just a little bit more because that double bond takes up a little bit more space than these single bonds, right? So that means that this bond angle here ideally was 120, but it's probably going to be a little bit less than 120. because it's going to be pushed together just a little bit. And we had one example like that where we were seeing it was maybe 116 on another similar example. But yeah, it'll be a little bit less than 120. Okay. Then lastly, we have this oxygen. Let's take a look at this bond angle between these two bonds. This has 4 domains, electronic domains, so it is tetrahedral electronic geometry. But in terms of its molecular geometry, it is bent since it has those 2 lone pairs. So ideally with tetrahedral, that would be 109.5. This will be less than 109.5 because those lone pairs take up some space. Okay. And maybe, like we had seen before, it's maybe about 104.5 if it's similar to water. It looks pretty similar to water, but I wouldn't bet on it being exactly 104.5, but a little bit less than 109.5. All right, lastly, molecular polarity. So this depends not only on the polarity of the individual bonds, but also on its molecular geometry. So we've already determined the polarity of individual bonds. That was based on the difference in electronegativity between the 2 atoms. So carbon and oxygen had a big enough change in electronegativity that we called it a polar covalent bond. So step 1 in determining molecular polarity, the molecule needs to have polar covalent bonds in order to be polar. If they have pure covalent bonds, they will be nonpolar. It does not matter the geometry. Just because an atom has polar covalent bonds, it does not mean that it will be polar, just because there are times in which these chemical bonds will essentially cancel each other out. So if we take a look at CO2 here we've drawn in the 2 vectors that are associated with the polar covalent bonds. Oxygen is more electronegative than carbon, and these are exactly 180 degrees from each other. So kind of like tug of war, these cancel each other out. So this CO2 ends up being a non-polar molecule, even though it has polar covalent bonds. Water, on the other hand, also has polar covalent bonds. Hydrogen and oxygen is a polar covalent bond. Again, the hydrogens are more positive than the oxygen. Oxygen is more electronegative, so the arrows are drawn towards the oxygen. But because it is bent, those vectors have a magnitude and a direction, and you can see they're kind of going both towards that oxygen. So this will have a net dipole. This will end up being polar. It has polar covalent bonds, and if you were to add those 2 vectors together, you would get a net dipole, a net vector going up towards that oxygen. So water ends up being polar. You can see there's similar situations. They both have just 2 atoms off the central atom, but it really matters what their geometry is. Here's another example. Let's say this is BF3, so boron in the center and 3 fluorines on the outside, let's say. These are polar bonds as well. But all of them are exactly the same magnitude. 1, 2, and 3 are all the same magnitude. So they, again, will actually cancel each other out. Again, you can kind of think about tug of war. If you had 3 different ropes all being pulled in those 3 directions, all exactly 120 degrees from each other, that central atom wouldn't move either. So these do actually also cancel each other out. So despite this having polar covalent bonds, this will also be a non-polar molecule. So that's true. This is trigonoplanar with no, and again, there's no lone pairs on that central atom. Tetrahedral, the same thing will occur. It's a little bit harder to see this probably, but those 4 bonds will cancel each other out. So this could be CF4, for example, carbon tetrafluoride, where there are 4 polar covalent bonds, but actually all 4 of them will cancel each other out. They're all equal in magnitude, and they're equally spaced out, so they will cancel each other out. This starts to change when you change individual locations, either changing one of them to a lone pair. That will change the geometry, just like we did with water in the upper right-hand corner, or if we change the identity of the atom. So here we replaced one of those atoms with a hydrogen, and now all of a sudden that carbon-hydrogen doesn't really have, it has a very, very weak dipole associated with it, but essentially it is not a polar covalent bond, right? It is a pure covalent bond. So now this new molecule is polar because we have replaced one of those atoms with something that has a different electronegativity. So this whole molecule will now be polar, even though it had the same geometry as this molecule right here, right? So you can see that there's lots of similarities. This one is non-polar in total. This one is polar. Okay. All right, so it's sometimes you will hear that just because something, once it has a lone pair on the central atom, it will become polar if it has polar covalent bonds. That is not always true, though it often is a good starting point in general. So yeah, this tends to be a trickier topic in general. Lastly, we have structural isomers. So these are molecules that have the same chemical formula but slightly different arrangements of the atoms. Here you have a double bond. There is no rotation around the double bond, so these are two distinct molecules. And this will end up affecting the polarity as well. So you could have times where one of these structural isomers will be polar and maybe the other one won't be. So you can see the one on the right is more polar because you have these strong polar covalent bonds at the bottom, where if you look at the molecule on the left, they're kind of canceling each other out. They're in opposite directions. So you can actually have discrepancies like this based on these structural isomers.